Right now, there's a number that cosmologists work with every single day, a number so staggering in its implications that even the physicists who use it routinely admit it keeps them up at night. That number is 10 to the power of 122. It represents the ratio between what our best theory of physics predicts about the energy of empty space and what we actually measure when we look at the universe. That is not a discrepancy of 10%. It is not a rounding error. It is the largest mismatch between theory and observation in the entire history of science, a gulf so vast that if you wrote it out as a decimal, you would fill every book ever written by humanity with zeros before reaching the first significant digit. And yet, this embarrassing number sits at the heart of the deepest mystery in all of physics. A mystery about something that fills every cubic centimeter of the universe. Something that is tearing the cosmos apart at an accelerating rate. Something that nobody, despite decades of brilliant effort by the finest minds our species has produced, can explain even slightly. Here is what will fundamentally alter the way you think about reality. The universe is not mostly made of the stars and galaxies you can see. It is not mostly made of the gas clouds drifting between them. It is not even mostly made of the exotic dark matter that holds galaxies together without emitting a single photon. 95% of everything that exists is something else entirely. Something invisible. Something that does not interact with light in any way we can detect. Something whose nature we cannot determine, whose origin we cannot explain, and whose future behavior we cannot reliably predict. And that something is winning. It is beating gravity. It is stretching space faster and faster with every passing moment. It is in the process of determining the ultimate fate of every star, every galaxy, and every atom in the observable universe. If you want to understand what the cosmos is actually made of and what it is doing to itself, consider liking and subscribing. It genuinely helps more than you know. Are you ready? Let's begin. The story of dark energy begins, like so many revolutions in science, with an observation that nobody wanted to make. In the early 1990s, two independent teams of astronomers set out to measure a number. They were fairly confident they already knew roughly what to expect. They wanted to pin down the deceleration parameter, a quantity describing how much the expansion of the universe was slowing down over time. The teams were not questioning whether expansion was slowing. That seemed obvious. The universe is full of matter. Matter has gravity. Gravity pulls things together. Of course, the expansion was slowing. The only real question was by how much, and what that rate implied about the ultimate fate of the cosmos. Both teams used the same cosmic measuring stick to conduct their surveys. A particular type of stellar explosion called a Type 1a supernova. When a white dwarf star accumulates enough mass from a companion, it reaches a precise critical threshold and detonates with an energy output so enormous it briefly outshines its entire host galaxy, sometimes releasing more energy in a few seconds than our sun will produce across its entire 10 billion year existence. The crucial property of these explosions for cosmology is that they all detonate at nearly the same mass threshold, which means they all reach nearly the same peak brightness. They are standardizable candles. Measure how bright one appears from Earth. Compare that to how bright it actually is, and you can calculate exactly how far away it is. Do this for enough supernovae across enough cosmic history, and you can map how fast the universe was expanding at different points in time. The High Z Supernova Search Team led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, spent years collecting these explosions. They observed supernova in galaxies billions of light-years away, meaning they were seeing the universe as it existed billions of years ago. They expected to find that the ancient universe was expanding faster than today, with gravity gradually putting the brakes on over cosmic time. What they found instead was so unexpected that both teams spent months checking and rechecking their data, convinced they had made a systematic error somewhere. They had not. The distant supernovae were dimmer than they should have been if expansion was decelerating. They were farther away than the deceleration model predicted. The expansion of the universe was not slowing down, it was speeding up. The 1998 announcement of this discovery landed in physics like a detonation. Astronomers and cosmologists around the world read the papers with a mixture of astonishment and disbelief. Einstein had actually introduced a term into his general relativity equations decades earlier, a cosmological constant he called lambda, specifically to allow for a static universe, one that neither expanded nor contracted. He had later called this his greatest blunder, when Hubble's observations revealed the universe was expanding after all, making the constant seem unnecessary. Now, suddenly, that blundered constant appeared to be real. There was something in space itself, some property of the vacuum, that was pushing outward against gravity with enough force to overcome it on cosmic scales. The teams won the Nobel Prize in Physics in 2011 for a discovery that nobody had set out to make. Astronomers needed a name for whatever was causing this acceleration, and they settled on dark energy. The name is mostly an admission of ignorance. It is dark because it does not emit, absorb, or reflect light in any detectable way. It is energy because it fills space and has consequences for the dynamics of the cosmos. Beyond that, the name tells you almost nothing, because almost nothing is known. Dark energy is not a substance in any conventional sense. You cannot collect it in a container. You cannot see it with any telescope. You cannot feel its presence in any direct way. Yet based on current measurements, it accounts for approximately 68% of the total energy content of the observable universe. The stars, galaxies, nebulae, and all the luminous matter that fills our night sky with light represents less than 5% of everything. Dark matter, the invisible gravitational scaffolding that holds galaxies together and whose existence is inferred from its gravitational effects, makes up roughly 27%. Dark energy swamps both of them combined. To appreciate what 68% of the universe being made of something completely unknown actually means, consider an analogy. Imagine you are a scientist studying the ocean. You have spent your career cataloging fish, measuring currents, analyzing water chemistry. You believe you have a reasonable understanding of what the ocean is and how it works. Then, someone tells you that 95% of the ocean's volume consists of a substance you have never sampled, cannot see, and have no instrument capable of detecting directly. You can only infer its existence from the fact that the ocean is behaving in ways your known physics cannot explain. That is the situation cosmology finds itself in. The universe we can see and measure directly is an almost negligible fraction of what actually exists. The simplest possible explanation for dark energy is that it is the energy of the vacuum itself. In quantum field theory, the framework that describes the behavior of particles and forces at the smallest scales, empty space is not truly empty. It is filled with quantum fields, mathematical structures that permeate all of space and whose fluctuations give rise to the particles we observe. Even in their lowest energy state, these fields are not silent. They vibrate constantly, producing what physicists call zero-point energy, a baseline hum of quantum activity that cannot be removed no matter how thoroughly you evacuate a region of space. The Casimir effect provides direct experimental proof that this vacuum energy is real. Place two uncharged metal plates extremely close together in a vacuum, and they will attract each other, pushed together by the difference in quantum fluctuations inside and outside the gap between them. The effect has been measured to extraordinary precision and matches theoretical predictions. Vacuum energy exists. The catastrophe emerges when you try to calculate how much of it there should be. Quantum field theory allows physicists to estimate the energy density of the vacuum by summing up contributions from all the quantum fields that exist. When you perform this calculation using the standard model of particle physics and integrate up to the energy scale where quantum gravity is expected to become important, the number you get is approximately 10 to the power of 113 joules per cubic meter. The number you actually measure when you infer the dark energy density from the universe's expansion rate is approximately 10 to the power of -9 joules per cubic meter. The discrepancy between prediction and measurement spans 122 orders of magnitude. Written as a ratio, the predicted value exceeds the observed value by a factor of 1, followed by 122 zeros. This is what physicists mean when they call it the worst prediction in the history of science. Not the most wrong by a small margin. The most wrong by a margin that has no precedent in human intellectual history. There are several possible responses to this catastrophe. The first is that the calculation is simply wrong in some fundamental way that requires new physics to resolve. Perhaps some undiscovered mechanism causes the enormous vacuum energy contributions from different quantum fields to cancel each other almost perfectly, leaving behind the tiny residual we observe. Supersymmetry, a theoretical framework that pairs each known particle with a heavier partner, was once hoped to provide such cancellation. But the Large Hadron Collider at CERN has found no evidence for supersymmetric particles at the energies where they were expected to appear. And while supersymmetry has not been ruled out entirely, the simplest versions that would most elegantly explain the cancellation problem appear to have been eliminated. What makes this particularly striking is the direction of change. The event horizon is not expanding to encompass more of the universe over time. It is shrinking. As dark energy drives accelerating expansion, more and more galaxies cross the event horizon and become permanently unreachable. The window of cosmic accessibility is not opening, but closing. Galaxies that sit just inside our event horizon today will be carried beyond it in the coming billions of years. Structures that astronomers could in principle visit with sufficiently advanced propulsion will become permanently forbidden territory. The accessible universe is shrinking with every passing moment, and this shrinkage will continue indefinitely as long as dark energy maintains its current behavior. Within roughly 2 trillion years, which is approximately 150 times the current age of the universe, the last of the galaxies in the local group outside our own gravitational neighborhood will have receded beyond the event horizon. Future astronomers inhabiting whatever merged galaxy descends from the collision of the Milky Way and Andromeda, which will occur in about 4.5 billion years, will look out into a universe that appears almost completely empty. The cosmic microwave background radiation, that faint thermal glow left over from the moment 380,000 years after the Big Bang, when the universe first became transparent and which currently bathe every square centimeter of space with roughly 400 photons, will have been redshifted to wavelengths so long that no plausible detector could register them. Every signature of the Big Bang accessible to observation will have been erased by the very expansion that our current measurements reveal. Those future astronomers, if they exist, will possess no evidence that 2 trillion galaxies once populated the observable universe. They might develop their own physics from scratch, observing only the stars of their merged home galaxy, and conclude correctly from all the evidence available to them that the universe contains only a single large galaxy surrounded by an infinite void. They would be wrong in the most profound possible sense. They would be missing 99-point-something% of cosmic reality, hidden from them by the mathematics of dark energy. It is worth pausing on this for a moment. We happen to live at a cosmologically special time. We are close enough to the Big Bang that the evidence of cosmic origins is still visible. We are far enough from the ultimate dark future that the universe still contains a rich tapestry of observable structure. Cosmologists 100 trillion years from now would be in a fundamentally worse epistemic position than cosmologists today, unable to discover what we can currently measure. The universe is slowly destroying its own evidence. The consequences for the large-scale structure of the universe are equally dramatic and begin on timescales somewhat shorter than the trillion-year disappearance of external galaxies. Gravitationally bound structures, groups and clusters of galaxies held together by their mutual gravity, resist the expansion locally. The Milky Way and the Andromeda galaxy, along with the approximately 50 smaller galaxies in our local group, are gravitationally bound and will remain so even as the universe expands around them. The Virgo cluster, approximately 53 million light-years away, appears to be marginally bound or marginally unbound, depending on measurements of its total mass and the precise value of the Hubble constant, one of the most actively debated numbers in modern cosmology. Even the Virgo supercluster, the larger structure of which our local group is an outlying member, may not survive indefinitely if dark energy maintains its current strength. This has led to the concept of the Great Isolation. As dark energy drives the expansion of space to ever larger scales, every gravitationally bound structure will eventually become an island. Our local group, merged into a single large elliptical galaxy in the far future, will be surrounded by a void of growing emptiness, separated from all other galaxies by distances that expand faster than light. Within that isolated island, the normal processes of stellar evolution will continue. Stars will form from remaining gas. Old stars will die. White dwarfs will cool. Neutron stars will spin down. Black holes will slowly evaporate through Hawking radiation over timescales that make the current age of the universe look like a brief prologue. But the cosmic context will be gone. The web of connections linking our galaxy to the universe at large will have been severed by the expanding void that dark energy creates. The possibility that dark energy is not constant, that it could change over time, introduces a much more dramatic range of potential futures. One of the more alarming possibilities is the Big Rip. In this scenario, the energy density of dark energy does not remain constant as the universe expands, but instead increases, becoming stronger per unit volume as space grows. This requires a specific form of quintessence called phantom energy, in which the ratio of pressure to energy density crosses a particular threshold. If this occurs, the consequences escalate in severity across cosmic time. First, the expansion of the universe accelerates, as it does today. Then, the acceleration becomes so extreme that even gravitationally bound structures begin to be pulled apart. Galaxy clusters dissolve first, their constituent galaxies separated by the expanding space between them. Then, individual galaxies are torn apart as the expansion overwhelms the gravity holding their stars together. Then, individual solar systems. Then, in the final moments of the Big Rip, even atoms would not survive. The electromagnetic force that binds electrons to nuclei would be overcome by the expanding space between them. The universe would end not in darkness or cold, but in a moment of perfect dispersal, every particle in the cosmos separated from every other particle by an unbridgeable and growing void. Calculations by physicist Robert Caldwell and collaborators place the time of the Big Rip, if phantom energy is real and maintains its current properties, at approximately 22 billion years from now. This is less than twice the current age of the universe. On the timescale of the cosmos, this is relatively imminent. In the final billion years before the Rip, the Milky Way would be torn from the local group. In the final months, the solar system would be disrupted. In the final minutes, Earth would be ripped apart. In the final fraction of a second, atoms would cease to exist. The universe would end not with a whimper, but with the most thorough dispersal of matter and energy physically conceivable. However, the Big Rip is currently not the favored scenario among cosmologists. Observations of the universe's expansion history suggest that dark energy's properties are consistent with a cosmological constant to within current measurement precision. No strong evidence for phantom energy has emerged from supernova surveys, galaxy clustering measurements, or any other observational probe. The most recent data from surveys like the Dark Energy Survey and preliminary results from Euclid suggest that dark energy is behaving like a cosmological constant, at least within the precision of current measurements. But the precision is not yet good enough to definitively exclude phantom energy, and the stakes are high enough that nailing down the answer ranks among the highest priorities in modern observational cosmology. A third possible future, less dramatic than the Big Rip, but more desolate than the cosmological constant scenario, involves dark energy weakening over time. In some quintessence models, the field driving the acceleration evolves toward a lower energy state, reducing the effective push against gravity. If dark energy fades completely, gravity would eventually win on the largest scales. The expansion would slow, stop, and reverse. Galaxies, liberated from the accelerating expansion, would begin falling toward each other under the influence of gravity. The merger of structures would accelerate. Temperature in the universe would rise as gravitational potential energy converted to heat, and the cosmos would ultimately contract toward a big crunch. This end point would be, in a sense, the mirror image of the Big Bang, an era of increasing density, temperature, and disorder, culminating in a singularity where our physics breaks down. Some theorists have proposed that such a singularity could bounce, initiating a new cycle of expansion, but this remains speculative physics far beyond what current theory can reliably predict. A fourth scenario, arguably the most philosophically challenging, emerges from models where dark energy flips sign, transitioning from a repulsive to an attractive contribution. In this case, the expansion would not just slow, but could reverse before gravity alone could accomplish the job, leading to a collapse that occurs sooner and more violently than simple gravitational attraction would produce. The timing and character of such a collapse would depend entirely on the dynamics of whatever field is responsible for dark energy, which returns us inescapably to the fact that we do not know what that field is or how it behaves. The second response is that dark energy is not vacuum energy at all. Perhaps it is a dynamic field that permeates space, not a fixed property of the vacuum, but something that can change over time. Physicists call this general class of possibilities quintessence, named after the ancient Greek concept of a fifth fundamental element beyond earth, water, fire, and air. In quintessence models, dark energy is a field with a value that slowly evolves as the universe expands, potentially taking different strengths at different points in cosmic history. This would mean the expansion of the universe is not accelerating at a fixed rate, but at a rate that can change, either speeding up further or eventually reversing, depending on how the field evolves. The distinction between a constant dark energy and a dynamic quintessence field has potentially enormous consequences for the ultimate fate of the universe, and it is currently one of the most actively pursued questions in observational cosmology. If dark energy is a cosmological constant, its energy density remains fixed as the universe expands. Matter and radiation dilute as space stretches, but the vacuum energy per unit volume stays the same, meaning dark energy becomes an ever larger fraction of the total cosmic budget as time passes. The expansion accelerates without limit, eventually tearing galaxies, stars, and eventually atoms apart in what theorists have called the Big Rip. If dark energy is instead a quintessence field that weakens over time, the acceleration might slow and could conceivably reverse, leading to different possible fates. Distinguishing between these possibilities requires measuring the expansion history of the universe with extraordinary precision across billions of years of cosmic time. This is precisely what missions like the European Space Agency's Euclid telescope, launched in 2023, and NASA's Nancy Grace Roman Space Telescope, planned for later in this decade, are designed to do. Both observatories will map the three-dimensional distribution of hundreds of millions of galaxies across cosmic time, measuring how the pattern of large-scale structure has evolved, and using that pattern to infer the expansion history of the universe with unprecedented accuracy. The pattern of galaxy clustering encodes information about the balance between gravity pulling things together and dark energy pushing them apart at every epoch in cosmic history. Reading that encoded information carefully enough might reveal whether dark energy has been constant or changing across the billions of years the universe has been accelerating. There is a specific signature these surveys are looking for, called baryon acoustic oscillations. In the early universe, before atoms could form, the cosmos was a hot, dense plasma in which sound waves propagated. These waves had a characteristic scale determined by the distance sound could travel in the roughly 400,000 years before the universe cooled enough for atoms to form and the plasma to become transparent. When that happened, the sound waves froze into the distribution of matter, leaving an imprint at a specific preferred separation distance between galaxies that is preserved in the large-scale structure of the cosmos today. By measuring this preferred separation at different cosmic epochs, astronomers can track how the expansion of the universe has changed over billions of years, providing one of the cleanest possible probes of dark energy's behavior. The Euclid mission will measure this separation across a volume of space more than 10 times larger than any previous survey, potentially revealing whether dark energy has stayed constant or shifted over the history of the universe. A third possible response to the dark energy problem is perhaps the most philosophically unsettling. Perhaps the vacuum energy really is as large as quantum field theory predicts, and we observe such a tiny remnant only because we exist in a special region of a vastly larger multiverse, where the cosmological constant takes different values in different regions. Regions with a large, positive cosmological constant expand so rapidly that matter never has time to clump into galaxies, stars, or planets. Life cannot form there. Regions with a large, negative cosmological constant quickly recollapse before any complexity can emerge. Only in a narrow range of values around what we observe can stars form, elements heavier than hydrogen be synthesized in, stellar interiors, planets assemble, and creatures capable of asking questions about dark energy come into existence. This is an anthropic selection argument. We necessarily find ourselves in a region where the cosmological constant permits our existence, even if that region is cosmically rare. This argument, associated particularly with the string theory landscape, a framework in which the equations of string theory admit an enormous number of possible solutions, each corresponding to a different vacuum with different physical constants, is controversial in ways that go beyond ordinary scientific disagreement. Many physicists find it deeply unsatisfying because it seems to abandon the quest for a unique, principled explanation of why the universe has the properties it does. If any value of the cosmological constant is realized somewhere in the multiverse, and we live where we do simply because we must, then the question of why dark energy has the value it does receives an answer that feels more like a shrug than an explanation. Critics argue that a theory capable of explaining everything in principle explains nothing in practice, since any observation can be accommodated by appealing to selection effects in the right region of the multiverse. Defenders counter that science has no alternative if the multiverse is what the mathematics actually demands. The string theory landscape is not a choice physicists made because they found it philosophically pleasing. It emerges from the mathematics of a theoretical framework developed to unify quantum mechanics and general relativity. If that mathematics genuinely predicts an enormous space of possible vacuum configurations, dismissing the conclusion because it feels uncomfortable does not make the discomfort scientifically justified. The question is not what we find satisfying, but what the universe actually does. And there is at least the beginning of a testable prediction. If the anthropic selection argument is correct and we live in an ordinary region of the multiverse, then we should find ourselves in a universe that is just barely capable of supporting the complexity required for observers. The value of the cosmological constant we measure, which sits just barely in the range that allows galaxies to form, is at least consistent with this prediction, though whether it constitutes genuine evidence for the multiverse remains hotly debated. Beyond the question of what dark energy is, lies the question of what it is doing to the universe right now and what it will do in the future. The acceleration caused by dark energy is not merely a curiosity for cosmologists. It is actively reshaping the observable universe on timescales that are enormous by human standards, but brief in the context of cosmic history. The most immediate consequence is the recession of distant galaxies. The universe expanded roughly 67 kilometers per second faster for every additional megaparsec of distance between 2 points, where 1 megaparsec equals about 3.26 million light-years. At distances beyond approximately 14 billion light-years, this recession velocity exceeds the speed of light. This does not violate special relativity, because space itself is expanding, not because any object is moving through space faster than light. The distinction is fundamental to understanding cosmic expansion. Special relativity prohibits objects from moving through space faster than light. It places no constraint on the rate at which space can expand. Two galaxies can recede from each other at superluminal rates without violating any physical law, as long as neither one is moving through its local space faster than light. Nevertheless, the practical consequence is the same as if a light-speed barrier existed. Light emitted from a galaxy currently receding at faster than light speed will never reach us, no matter how long we wait. Those galaxies are already beyond our cosmological event horizon, permanently cut off from any future interaction. The cosmological event horizon currently sits at approximately 16 billion light-years. This is not the edge of the observable universe, which at 46.5 billion light-years extends considerably farther and represents the maximum distance from which light could have reached us over the entire age of the cosmos. The event horizon is a more restrictive boundary. It marks the maximum distance from which a signal sent today could ever reach us in the infinite future, given that dark energy will continue accelerating the expansion. Any galaxy currently beyond 16 billion light-years is not merely distant, it is permanently inaccessible. No signal we send can ever reach it. No signal it sends can ever reach us. Not now. Not in a billion years. Not ever under any circumstances consistent with known physics. The measurement of dark energy's properties is complicated by a crisis that has developed within cosmology over the past decade. The Hubble constant, the number describing the current rate of cosmic expansion, can be measured by two fundamentally different approaches that are producing results in increasing disagreement with each other. The first approach uses the cosmic microwave background, measuring tiny fluctuations in the temperature of this ancient light to infer the physical conditions of the early universe and extrapolate forward to today using the standard cosmological model. The Planck satellite's measurements using this approach yield a Hubble constant of approximately 67 kilometers per second per megaparsec. The second approach builds a distance ladder, calibrating nearby distance measurements using Cepheid variable stars, whose pulsation periods are tied to their luminosity, and then using Type 1a supernovae as standardizable candles to measure the expansion rate in the nearby universe directly. This approach, refined by teams including the SH0ES collaboration led by Adam Rees, one of the original discoverers of dark energy, consistently yields approximately 73 kilometers per second per megaparsec. The gap between 67 and 73 may not sound enormous, but it represents a discrepancy of roughly 9% that has persisted and grown as both measurements have been refined. A 9% disagreement between two independent measurements of the same quantity, both claiming precision at the few percent level, is a significant tension in any branch of physics. In cosmology, where the standard model has been extraordinarily successful at explaining a huge range of observations, it amounts to a crisis. Either one or both measurements have unidentified systematic errors, or the standard cosmological model is missing something important. Some physicists have proposed that early dark energy, an additional component that was briefly significant in the early universe before fading, could explain the discrepancy. Others have suggested modifications to the dark matter model, or even to the fundamental equations of gravity. The Hubble tension, as it has become known, may be the first sign that our cosmological model requires revision in ways that could reshape our understanding of dark energy and the universe's fate. The tension has intensified with results from the James Webb Space Telescope. Webb has independently calibrated the distance ladder using Cepheid stars and galaxies far more distant than previously possible, cross-checking the measurements that underpin the local Hubble constant value. The early Webb results suggest that the local measurement is not simply an artifact of calibration errors in nearby Cepheid measurements, reinforcing the conclusion that the tension is real and not a measurement artifact. If the discrepancy cannot be explained by systematic errors, cosmology needs new physics. What that new physics might be, and how it relates to dark energy, remains an open question that will likely define much of theoretical and observational cosmology across the next decade. There's another approach to understanding dark energy that operates not by looking outward at distant galaxies, but by examining the microscopic structure of space-time itself. Some theorists have proposed that the accelerating expansion is not caused by a new energy component at all, but rather by a modification of general relativity at the largest scales. On the scales of solar systems and individual galaxies, general relativity has been tested with extraordinary precision and found to be in perfect agreement with observation. Gravitational wave detections by LIGO and Virgo, measurements of the orbital decay of neutron star binaries, the direct imaging of black hole shadows by the Event Horizon Telescope. All these confirm that Einstein's equations work exactly as predicted in the strong field and highly dynamical regimes. But on scales comparable to the size of the observable universe, general relativity has been extrapolated far beyond the conditions in which it has been directly tested. Perhaps it requires modification at these cosmic scales, and perhaps that modification naturally produces an apparent accelerating expansion without requiring a dark energy component at all. Modified gravity theories, including extensions of general relativity called FR gravity, in which the equations of space-time curvature include additional terms beyond Einstein's original formulation, and scalar tensor theories, in which an additional scalar field couples to the curvature of space-time, can in some cases reproduce the expansion history of the universe without invoking dark energy as a separate component. The challenge is producing a modified gravity theory that explains the observed expansion without also predicting deviations from general relativity on scales where the equations have been precisely tested. So far, no modified gravity theory has succeeded in matching all the observational data, as well as the standard model, with a cosmological constant, but the search continues, and future surveys like Euclid will provide powerful tests of whether gravity behaves on cosmic scales exactly as Einstein's equations predict. One of the more intriguing observational probes of dark energy exploits a phenomenon called weak gravitational lensing. Gravity bends light, and the mass distributions of galaxies and galaxy clusters curve the paths of photons passing near them, distorting the apparent shapes of more distant galaxies behind them. By measuring the statistical pattern of these shape distortions across millions of galaxies, astronomers can map the distribution of all matter, including dark matter, across large regions of the universe. How that distribution evolves with time depends on the balance between gravity and dark energy. A cosmological constant produces a specific pattern of structure growth. A dynamic dark energy field with different properties produces a different pattern. Measuring the pattern with sufficient precision across cosmic time constrains the nature of dark energy with a complementary probe independent of supernova distances, or CMB fluctuations. The Dark Energy Survey, which operated from 2013 to 2022 and imaged approximately 300 million galaxies, produced some of the most powerful weak lensing constraints on dark energy and the growth of cosmic structure to date. Its results were broadly consistent with the standard cosmological model, but not precise enough to discriminate between a cosmological constant and many quintessence alternatives. Euclid and the Vera Rubin Observatory's Legacy Survey of Space and Time, which will begin its 10-year imaging program in the coming years and eventually catalog approximately 20 billion galaxies, will increase this constraining power by an order of magnitude or more, potentially revealing whether dark energy is truly constant or showing signs of evolution. The question of dark energy ultimately connects to some of the deepest unsolved problems in theoretical physics. Quantum field theory and general relativity are the two most successful theories in the history of science, each confirmed by experiment to extraordinary precision in their respective domains. Yet they are fundamentally incompatible with each other. General relativity describes space-time as a smooth, continuous fabric that curves in response to mass and energy. Quantum mechanics describes fields and particles in terms of discrete, probabilistic processes that operate within a fixed space-time background. These two pictures cannot both be exactly right because they start from incompatible assumptions. A true theory of quantum gravity, one that reconciles the quantum behavior of matter and energy with the dynamical geometry of space-time, does not currently exist. Despite decades of effort by thousands of physicists in frameworks including string theory, loop quantum gravity, and causal dynamical triangulation. Dark energy sits precisely at the intersection of these two incompatible frameworks. It is a property of space, which belongs to the domain of general relativity, but its magnitude and the fact that it differs by 122 orders of magnitude from the quantum field theory prediction suggests that understanding it requires reconciling quantum mechanics with gravity in a way that resolves the catastrophic discrepancy. The cosmological constant problem is, in the view of many physicists, not merely a puzzle within cosmology, but a symptom of the deepest incompleteness in our fundamental understanding of nature. Solving it would likely require discoveries as profound as general relativity or quantum mechanics themselves. This is worth sitting with for a moment. We are not talking about a subtle correction to an otherwise complete picture. We are talking about 68% of the universe being composed of something we fundamentally cannot explain. We are talking about a prediction that our best theories make being wrong by a factor so large it has no precedent. We are talking about a force that is currently determining the ultimate fate of every structure in the observable universe, from the nearest galaxy clusters to the most distant objects reachable by light, operating through a mechanism that physics cannot currently describe. Dark energy is not a detail. It is not a footnote. It is the dominant component of the universe we live in, and it is almost entirely mysterious. The irony is that it is also, in some ways, the most precisely measured thing in modern cosmology. The equation of state of dark energy, a number describing the ratio of its pressure to its energy density that determines how it affects cosmic expansion, has been constrained to be within a few percent of the cosmological constant value of -1 by multiple independent observational probes. The amount of dark energy in the universe is known with similar precision from the cosmic microwave background. We know with considerable confidence how much dark energy there is and how it is behaving right now. What we do not know is what it actually is, why it has the value it does, whether it will remain constant or change, and what its ultimate fate will mean for everything else in the universe. There is something almost vertiginous about this situation. The universe does not hide its most important feature. Dark energy is not lurking in some exotic corner, accessible only to the most powerful accelerators or the most sensitive instruments. It is everywhere, in every cubic centimeter of space, operating continuously, determining the trajectory of the cosmos on the largest possible scales. You are surrounded by it right now as you read these words. Every cubic centimeter of the room around you contains dark energy, pushing on the boundaries of that cubic centimeter, trying to expand the space within it outward. The effect is completely negligible on human scales, where gravity and electromagnetism dominate overwhelmingly. But integrated across the billions of light years of the observable universe, the accumulated push of dark energy in every cubic centimeter of that incomprehensible volume exceeds the gravitational pull of all the matter in the cosmos. It has already won the large-scale competition between gravity and expansion. It has been winning for roughly 5 billion years, since the universe was approximately 9 billion years old, and dark energy's share of the cosmic energy budget first exceeded that of matter. Future observatories will push our understanding of dark energy in several directions simultaneously. Space-based spectroscopic surveys like Euclid will measure galaxy spectra, determining their distances and velocities with great precision across unprecedented volumes of the universe. Ground-based imaging surveys like Rubin will map galaxy shapes across the sky to depths never previously achieved. The Square Kilometre Array Radio Telescope, under construction in South Africa and Australia, will measure the distribution of neutral hydrogen gas in galaxies out to cosmological distances, providing yet another independent probe of how structure has grown in the presence of dark energy. The Nancy Grace Roman Space Telescope will combine the depth of Hubble with a field of view roughly 100 times larger, enabling supernova surveys and weak lensing measurements far more powerful than anything previously achievable from space. If these surveys find that dark energy is indistinguishable from a cosmological constant to their limit of precision, the mystery deepens. We will have confirmed that dark energy is extraordinarily well described by a constant energy density in space, while still having no explanation for why that constant has the value it does. If the surveys find deviations from a cosmological constant, it means dark energy is dynamic. It evolves over cosmic time, and the cosmological constant is not the correct description. This would be an extraordinary discovery, potentially providing the first empirical guidance about the nature of dark energy beyond its current energy density. It would motivate entirely new theoretical directions and potentially bring the resolution of the cosmological constant problem within reach. The possibility that dark energy is a new scalar field pervading the universe also raises a connection to the early universe that is fascinating to consider. Cosmic inflation, the period of exponentially rapid expansion in the first tiny fraction of a second after. The Big Bang that explains the remarkable uniformity and flatness of the universe is also believed to have been driven by a scalar field, commonly called the inflaton. The physics of inflation and the physics of dark energy share deep structural similarities. Both involve a scalar field driving accelerating cosmic expansion. Both require a field with specific properties regarding the ratio of pressure to energy, density. Some theorists have explored the possibility that these two episodes of accelerating expansion, separated by nearly 14 billion years of cosmic history, might be related to the same underlying physics, with the inflaton field somehow connecting to whatever field drives the current acceleration. These theories go by names like quintessential inflation and have not achieved broad acceptance, but they represent one direction in which theorists are searching for a unified explanation. The search for dark energy's origin also motivates investigations into the quantum vacuum from a completely different direction. Laboratory experiments using precision measurements of the Casimir effect, which directly probes the energy density of the quantum vacuum between closely spaced surfaces, have been refined to increasing sensitivity. Exotic materials, including metamaterials that interact with quantum vacuum fluctuations in unusual ways, are being studied. Some researchers have proposed that the discrepancy between the theoretical and observed vacuum energy could be explained if space-time has a fundamental discreteness at the Planck scale, a smallest possible unit of length of approximately 10 to the negative 35th meters, that introduces a cutoff in the quantum field theory calculation that brings the vacuum energy down to the observed value. Whether this approach is correct cannot currently be tested, but it illustrates the range of ideas being pursued as physicists search for a way to make sense of the number that should be there and the number that is. The ultimate fate of the universe depends more on what dark energy is than on almost any other single factor in cosmology. If it is a true cosmological constant, the future is one of accelerating isolation, followed by the slow heat death of each gravitationally bound island, stars exhausting their fuel, black holes evaporating across timescales that dwarf anything comprehensible, and a final state of maximum entropy in which nothing of note ever happens again. If dark energy is phantom energy that grows stronger, the Big Rip tears everything apart in a finite time. Roughly 22 billion years from now, if current estimates hold. If dark energy is quintessence that fades, gravity eventually wins, and the Big Crunch recollects the cosmos into a singularity. The equations of physics give us the framework to work out what each scenario implies. They do not tell us which scenario actually applies. We are creatures who appeared on a small planet orbiting an ordinary star in one of 2 trillion galaxies, in a universe that is 5 parts dark energy to 1 part dark matter to a sliver of everything we can see and touch and breathe. We have been asking questions about nature for perhaps 10,000 years. We have been doing systematic physics for perhaps 400. In that brief span, we have worked out the equations that describe the quantum behavior of every known particle, the geometry of space-time in the presence of any amount of mass and energy, and the thermal history of the universe from fractions of a second after the Big Bang to the present moment. We have detected gravitational waves from colliding black holes a billion light-years away. We have imaged the shadow of a black hole 65 million light-years distant. We have mapped the 3-dimensional distribution of galaxies across billions of light-years of cosmic history. And we have discovered, at the center of everything, a mystery so fundamental that solving it would require advances in our understanding of nature, as profound as anything that has come before. Dark energy is not the universe's most dramatic feature. It does not explode like supernova, or consume matter like black holes, or produce the dazzling light shows of nebulae. It operates quietly, invisibly, persistently, filling every corner of space with a gentle outward push that, integrated across the cosmos, overwhelms everything else. It is the dominant fact about the universe we inhabit, and it is almost entirely unknown. What that means, what it demands of us as a species that asks questions, is not despair about the limits of knowledge, but something closer to the opposite. The fact that 68% of the universe remains genuinely mysterious means that our understanding of nature is not nearly as complete as the textbooks might suggest. It means that discoveries of the first magnitude, revisions as fundamental as general relativity or quantum mechanics, remain to be made. The equations that will ultimately explain dark energy do not yet exist. The experimental results that will definitively identify its nature have not yet been collected. The theoretical framework that will reconcile quantum mechanics with gravity and explain the cosmological constant problem without appealing to a multiverse or a lucky cancellation has not yet been constructed. Someone alive today might live to see the first cracks appear in the dark energy mystery. The next generation of surveys might reveal that dark energy is evolving, providing the first empirical fingerprint of whatever field drives the acceleration. The Hubble tension might be resolved by the discovery of new physics in the early universe that reshapes the entire cosmological model. A breakthrough in quantum gravity might provide a natural mechanism explaining why the vacuum energy is so small, or the mystery might persist for generations, waiting for a revolution that nobody can currently anticipate. The universe has spent 13.8 billion years getting to the point where it contains creatures capable of asking what it is made of. The answer, it turns out, is mostly something we do not understand at all. That is not a failure. That is an invitation to understand just how consequential the dark energy discovery was. It helps to appreciate what cosmologists thought they knew in the early 1990s, before the supernova surveys upended everything. The prevailing view held that the universe contained enough matter, including dark matter, to eventually halt its expansion. The question was not whether gravity would win, but when. Different measurements of the total matter density pointed in different directions, some suggesting the universe would expand forever at a decelerating rate, others suggesting it might eventually recollapse. But nobody seriously entertained the possibility that the expansion was not slowing at all. The idea that it might be speeding up would have seemed, to most cosmologists of that era, not merely wrong, but physically nonsensical. Gravity attracts. Everything with mass or energy gravitates toward everything else. How could the universe possibly be accelerating outward? The answer required a conceptual step that Einstein had actually already taken and then retreated from. In general relativity, the relationship between energy, pressure, and the expansion of space is not the same as the relationship in Newtonian gravity. In Newtonian physics, only mass matters for gravity. In general relativity, pressure also contributes to the curvature of space-time, and hence to the gravitational dynamics of the universe. For ordinary matter and radiation, both the energy density and the pressure are positive, and both contribute to decelerating the expansion. But if something exists with a large negative pressure, something that pulls inward on itself, even as it has positive energy density, the pressure term in Einstein's equations can dominate over the energy density term and produce net acceleration rather than deceleration. A cosmological constant has exactly this property. Its pressure is equal in magnitude to its energy density, but opposite in sign, and this specific ratio produces an acceleration that grows stronger as the energy density of matter dilutes while the vacuum energy density remains constant. This is the physical reason why the cosmological constant, or any dark energy component with similar properties, drives acceleration. It is not that the vacuum energy is repulsive in any simple sense. It is that in the equations of general relativity, sufficient negative pressure can overwhelm the decelerating effect of energy density and drive space to expand faster with time. Understanding this mechanism requires abandoning the intuition that only masses matter for gravity, an intuition that serves perfectly well for the solar system and most ordinary astrophysical contexts, but fails when applied to the universe as a whole on its largest scales. The observational evidence for dark energy has grown far beyond the original supernova surveys in the quarter century since the discovery. The cosmic microwave background provides independent and extraordinarily precise confirmation. The pattern of tiny temperature fluctuations in this ancient light, imprinted when the universe was just 380,000 years old, encodes information about the total energy content of the cosmos at that moment and how it was distributed between matter, radiation, and any additional components. The fits to this pattern by the Planck satellite require a dark energy component making up roughly 68% of the total energy budget with extraordinary statistical precision. Remove dark energy from the model, and the fit to the observed pattern deteriorates badly. The CMB independently demands that something like dark energy exists. The large-scale structure of the universe provides a third independent confirmation. The way galaxies are distributed across space, in a cosmic web of filaments, sheets, and nodes separated by vast underdense voids, reflects the balance between gravity and dark energy throughout cosmic history. Gravity pulls matter together into denser regions. Dark energy resists this collapse on the largest scales, preventing the cosmic web from becoming denser and more tangled over time. Models that include dark energy reproduce the observed statistical properties of galaxy clustering with impressive accuracy. Models without dark energy produce large-scale structure that disagrees with observation. Every independent probe that cosmologists have applied to the problem points to the same conclusion. The universe is dominated by dark energy, and that dark energy is behaving like a cosmological constant with a value approximately 10 to the power of -9 joules per cubic meter. The fact that three entirely independent observational approaches, supernova distances, CMB fluctuations, and large-scale structure, all agree on the same dark energy density is one of the most powerful pieces of evidence in the history of cosmology. This is not a single measurement that could be dismissed as a systematic error or a fluke. It is a convergence of independent approaches, each sensitive to completely different aspects of the universe's behavior, all pointing to the same number. This convergence is what gives cosmologists confidence that dark energy is real, even in the absence of any direct detection or physical understanding of what it actually is. One consequence of dark energy that deserves attention is its effect on our ability to do cosmology at all. We exist at a fortunate moment in cosmic history, a time when the universe is old enough to have formed complex structure, but young enough that the evidence of its origins is still legible. The cosmic microwave background, that faint thermal glow from 380,000 years after the Big Bang, still bathes the entire sky with nearly uniform temperature, providing a direct window onto the conditions of the early universe. The distant galaxies we observe with our most powerful telescopes show us the universe as it existed billions of years ago, allowing us to construct a fossil record of cosmic history. The large-scale structure of the universe carries imprints of processes that operated in the first microseconds of existence, readable in the statistical patterns of galaxy clustering. All of this evidence is temporary. Dark energy is erasing it. As the universe continues to expand under dark energy's influence, the photons of the cosmic microwave background are being stretched to longer and longer wavelengths, their energy diluted, their temperature dropping. Today, the CMB temperature is approximately 2.7 degrees above absolute zero. In a trillion years, it will be so cold and so dilute that no instrument could detect it. The supernova that cosmologists use to map the universe's expansion history are happening in galaxies that are receding from us. Their light redshifted to longer wavelengths, their apparent brightness diminishing. In the far future, even the nearest external galaxies will have receded so far that their supernovae will be too faint and too redshifted to observe. The evidence that allowed us to discover dark energy in the first place is being removed from the universe, as the expansion dark energy stretches space and dims every distant source. This makes our current epoch uniquely valuable for understanding the cosmos. We happen to exist at a time when enough evidence remains visible to reconstruct the history of the universe from the Big Bang to the present. This window will not remain open forever. The same physics that produced the accelerating expansion we detected in 1998 is in the process of closing the book on observational cosmology, on timescales that are long by human standards but brief in cosmic terms. In 100 billion years, the book will be closed. In a trillion years, it will be as if it never existed. We have our window now, and the question of how to use it most effectively to understand the nature of the 68% of the universe we cannot explain is among the most important questions science has ever faced. Dark energy also raises a question that goes beyond physics into something approaching philosophy, though it has genuine scientific content. Why now? The energy density of dark matter decreases as the universe expands, diluting as matter spreads across a larger volume. The energy density of radiation decreases even faster, dropping with both the expansion of volume and the redshifting of individual photons to lower energies. The energy density of dark energy, if it is a cosmological constant, stays fixed at its current value regardless of how the universe expands. This means that early in the universe's history, matter and radiation dominated the energy budget, while dark energy was negligible. In the future, as matter and radiation continue to dilute, dark energy will become an ever larger fraction of the total. We happen to live at the cosmological moment when matter and dark energy are within roughly an order of magnitude of each other, neither completely dominant, both cosmologically relevant. This coincidence has a name among cosmologists. It is called the coincidence problem, or sometimes the why now problem. Of all the cosmic epochs in the universe's history, past and future, we find ourselves in the brief period when the energy densities of matter and dark energy are comparable. If dark energy had the same value but matter had been much more or less abundant, we would live in an era where either matter or dark energy overwhelmingly dominated, and the other was utterly negligible. Some physicists find this suspicious, a sign that either our cosmological model is missing something important or that anthropic selection is operating, allowing only in matter-dark energy comparable epochs complex enough for observers to exist. Others argue it is simply a coincidence with no deep significance, a quirk of our cosmic timing that needs no special explanation beyond the fact that we are here to notice it. The debate remains unresolved. The discovery of dark energy in 1998 was more than the addition of a new component to the cosmological inventory. It was a revelation that the universe is not doing what we expected, that our theories of its contents and dynamics were missing something fundamental, and that the simplest possible extrapolation of the physics we understand fails catastrophically when applied to the question of why the vacuum has the energy density it does. A quarter century of extraordinary observational and theoretical effort has confirmed the existence of dark energy, pinned down its current properties with impressive precision, and provided no satisfying explanation for what it actually is. The universe is mostly unknown, not mostly unexplored, as in there are regions we have not yet sent telescopes to examine. Mostly unknown, as in the dominant component of everything that exists is something whose fundamental nature remains beyond the reach of our current theoretical frameworks. That is the situation cosmology finds itself in at the beginning of the 21st century, and it is, depending on your disposition, either the most humbling or the most exciting fact in all of science. The equations that will eventually explain dark energy, that will reconcile the quantum vacuum with the observed cosmological constant, that will tell us what the universe is actually made of and why, do not yet exist. The experiments that will provide the decisive empirical guidance to point towards those equations are either just being built or are still being designed. The discovery that will restructure cosmology around a coherent picture of dark energy and its origin has not yet been made. We are, in the most literal possible sense, in the middle of the story. The chapter on dark energy is not just unfinished, it has barely begun. The universe has been here for 13.8 billion years. It will be here, in one form or another, for an immeasurably longer time. We have been asking systematic questions about it for roughly 4 centuries. The fact that those 4 centuries of inquiry have led us to the edge of the biggest mystery we have ever encountered is not a sign that science has reached its limits. It is a sign that science is working exactly as it should, pushing into territory where the familiar runs out, revealing the shape of what is not yet known, and pointing toward the discoveries that have not yet been made. The accelerating universe is the universe telling us something. We have not yet understood what.